Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. So in Module 3, we're going to talk about the scheduling of processes. Now recall, in Module 2, we discussed the concept of processes. So in a multi-programming environment, the operating system can support multiple processes concurrently. Now, in that case situation, the operating system needs to decide which process should be able to running and which process should be removed from the CPU so the other process can run. So the operating system needs to decide, the executions of these processes. Okay, so in particular, in the time sharing, the operating system needs to decide, okay, it's time to run the process. And then after for a while, the operating system needs to decide, okay, it's time to switch to another processes. Now, how does the operating system do this? So operating system is going to do this through the scheduling algorithm. Okay, that's something we're going to talk about in Module 3. So the first section, section 3.1, we first going to talk about the principles of scheduling. Now, scheduling decisions are made at the two different levels. One is called long-term scheduling. The other one is short-term scheduling. Now, for many operating systems, once a process is created, they will not immediately put the process into the ready list to fight for the CPUs. Remember the ready list we just discussed in the previous module. Okay. So instead, once a process is created, these operating systems will assign a state called a new. Okay, so they're not going to assign the process to ready state, but instead they're going to assign the process to new state, and then let the long-term scheduling to decide whether the process should be moved to the ready list or not. Okay. Now, once the long-term scheduling decides that this process should be moved to the ready list, okay, then the short-term scheduling will kick in. Now, the short-term scheduling is going to decide which process should be allocated to CPU and which process should be removed from CPU. So the short-term scheduling is going to move a process back and forth between ready list and the CPU. Okay. So when a running process becomes blocked, okay, for whatever reason, if they are waiting for resources, right? So the process is going to be put in the waiting list for a resource. So then the process will be blocked. And when the resource is ready, so the short-term, and then the process will be put back into the ready list. And the short-term scheduling going to decide whether the process will get the CPU again, okay, or not. Now, in another case, if the process is suspended, it will be moved to the suspended list. Okay. Or if a process will be removed from the suspended list. That's all the jobs that the short-term scheduling gonna do. Now from Module 2, we just learned that an operating system manages the processes using a function called the scheduler. Now, the scheduler function may use two different algorithms. One is called a non-preemptive scheduling algorithm. The other one is preemptive scheduling algorithm. Now, a non-preemptive scheduling algorithm allows the running process to continue until the process terminates or blocks on a resource, while the preemptive scheduling algorithm may stop the currently running process and choose another process to run. Now let's take a look at a simple example. Suppose, let's first talk about a non-preemptive. So the non-preemptive will allow the current process to finish before the scheduler load the next process. So let's say if I have a process 1, now process 1 is created at a time 1. Now if process 1 is the only process running, so the process 1 gets the CPU. Okay, now at the time 2, if another process is created at the time 2, now since this is non-preemptive, it really doesn't matter, right? If as far as process 1 is not finished, then process 1 going to continue. And while the process 2 has to wait. So I need to use the dotted line, means process 2 is waiting until process 1 complete its job at the T3. So then the process 2 will be allocated the CPU. Now that's non-preemptive. So process 2 cannot start until the process 1 completes its job. Now let's take a look at the preemptive. Preemptive running a scheduling algorithm. Now with the same scenario, suppose P1 is created at the time 1, and the P1 gets the CPU and start to run. Now at the time 2, P2 is created. So now the scheduler actually faces the situation. There are two processes, P1 and P2. Now the scheduler need to decide which one should be running. Now scheduling algorithm can decide based on the algorithm scheduling algorithm. So that's something we're going to talk about later. Now if the scheduling algorithm believes that the P1 has a higher priority than P2, so then in that case P1 going to continue, okay, until P1 complete the job, and then P2 will be loaded. Now if the scheduling algorithm believes that the P2 has higher priority, then it will stop the P1 and start to load the P2. So P2 going to be running, and then until P2 finish the job at T3, and then the process 1 going to be resumed. Okay, now at any particular point, the scheduler going to decide which one going to be running, whether I need to kick the currently running process or not. Now that decision is made under these three circumstances. 1, a new process enters the ready list, or a previously blocked or suspended process re-enters the ready list, or like in the time sharing, the operating system periodically interrupts the current running process to give other process a chance to run. So that's most likely the time sharing. The operating system running the time sharing. Now, each time when the scheduler of an operating system decides which process will be picked to run, then the priority of the process will be used. The scheduling algorithm is going to pick the process with the highest priorities and load this process into the CPU. Now, the priority of a CPU is a numeric value that indicates the importance of the process relative to the other processes. So the scheduler uses this value to decide which process to run next. Okay. Now, a priority can be a constant value. So once the process is created, a constant value is assigned to the process, which basically determines the priority of the process. Or sometimes a dynamic value will be used. So that means the priority of the process is changing. Okay, why this happens? So we can talk about it a little bit later in the next slide. So if the operating system needs to decide which process to run, if all the process has the same priority, typically the arbitration rule will be used. Okay. So we have learned that for all the processes in the ready list, the short-term scheduling should be used to determine which process should be selected to run. So which process should be put in the CPU. Or the short-term scheduling also determines which process should be removed from the CPU and put it back to the ready list. Okay, so the short-term scheduling algorithm is going to use the priority of each process to make such a decision. So if it's time for the short-term scheduling to decide, which process should run next, then the algorithm is going to check which one has the highest priority. Now the question is, how can we determine what is the priority for each of the processes? Okay. Now on the table, so we can see all these parameters we use to determine the short-term priority. Now one of these parameters is called arrival time. Now what is arrival time? Arrival time is the point in time when the process enters the ready list. Okay. And the departure time is the point in time when the process leaves the ready list by entering the blocked or suspended state or by terminating all work. So now let's take a look at the diagram here. Let's say I'm going to draw the diagram here. That's a timeline. Once the process is created, it will be initially in a new state, right? So at this point, the long-term scheduling algorithm is going to be used to determine whether this process should be put in the ready list. Okay, if the long-term scheduling algorithm decide that this process should be in the ready list, then the state will be changed to ready, and the process is going to be put in the ready list. Now, that's the time when the process enters the ready list, right? So that's arrival time. Now, when the process is in the ready list and it gets a chance to run. So it's determined by the short-term scheduling algorithm, and it determines that it's time for this process to run. Now the process is going to be in the running state. Okay. So then the process may be in the blocked state. So if the process is running and request for a resource, and then resource is not available, so the process will be blocked. It cannot continue to run. So if it's blocked, then it will be leave the ready list, and the process is going to be put in the waiting list for this resource. Okay, so this is called the departure time. Okay, now it's possible that once the process in the blocked state and suddenly it just get the resource. Okay, so it just get the resource, so it's ready to run. So then it will be back to the ready state. So the state is going to be changed to ready again. Now this time it's actually enters the ready list again. So that's another arrival time. And once in the ready state, it may actually change to running state if the CPU is available for this process. And after you finish the execution of some of the processes, and it will be back to the ready state. And then back to the running state. And then blocked again. And then back to the ready state. Running state, right? So this is the arrival time, and this is the departure time. And this is the arrival time again, and then it's in the ready state, in the running state, but it never leaves the ready state. Okay, continue to back to the ready state, and in the ready running state. Even it's in the running state, it's still in the ready list until the process is blocked again. So then it just leaves the ready list. So that's the departure time again. And then that's arrival time again. Okay. So you may have, multiple arrival time. Okay. And it may have a multiple departure time. Okay. So that's a definition for the arrival and departure. Now, what's attained CPU time? For attained CPU time, we need to figure out, suppose the CPU, we check at a certain point, this point. Now, at this point, we want to check what's the attained CPU time now. So the attained CPU time is the amount of CPU time used by process since arrival. Okay. So if we check this particular time point, then what's the nearest arrival time? It's here, right? There's another arrival time, but that arrival time is, before this one. So the attained CPU time gonna count, since the arrival time, the last arrival time, and the amount of amount of CPU time used by the process. So what is the CPU time used? So if it's in the ready state, now this time period, the CPU time is not used, right? Okay. So now only when it's in the running state. Let me actually change the color. Okay. So we can actually clearly see what's the differences. So now only during the time period when the process is running, now this is the time that the amount of CPU time used. And then from up to this point, then so here's a ready again, so that CPU is not used. And now up to this point, it's changed to running again. So that means, it acquires the CPU again. So this is again the CPU time used. So the amount of CPU time used is the addition of this time period and this time period. So that's the attained CPU time. Okay. Now what's the real time in the system? So by definition, the real time in system is the amount of actual time the process has spent in the system since arrival. The amount of actual time the process has spent in the system since arrival. Okay. So now if you actually count this, timeline, so what's the arrival time here, right? This is the nearest arrival time. So the real time used in system is the actual time the process has spent in the system since arrival. So that's this. It doesn't matter whether it's in the ready state or running state. It's the amount of actual time the process has spent in the system. So it doesn't have to be in the CPU, but in the system. So that's the real time in the system. Okay, so that's this. Now what's the total CPU time? The total CPU time is basically the amount of CPU time the process will consume between arrival and the departure. Okay, so in that case, let me change the color again. So that's the total CPU time, the amount of CPU time the process will consume between arrival and the departure. Now, when we talk about this arrival and departure time period, okay, so in this time period, what is the amount of CPU time? It's not a whole line, okay, only the period of time the process is using the CPU. And then the other time that is running. So that's these two areas put together, that's the total CPU time. Now the real time is, between the arrival and this timeline, but the total CPU time is they basically count from the arrival to the departure, between arrival and departure, and the total CPU time. Now this is in the ready state, so it's actually in the ready list, right? It's not in the CPU, but this period of time it's in the CPU. Okay, so that's the definition for each of these parameters. And then what is the external priority? So external priority is some kind of priority we can assign to the process, which is not related to the characteristic of the process. For example, once the process is created, then we can assign the external priority. For example, if the process is created by the kernel, by the operating system, then you may assign a very high priority number. And if it's created by user, like a user application, then the external priority could be lower. So that's the fact we're going to use to decide what's the external priority. Now the deadline normally apply to the real-time operating system. Now, some of the operating systems are called the real-time operating system. So that means once the process is created, you have to complete all the instructions for the processes within certain time period. So there's a time constraint. Now, this is important. For example, the operating system used in the nuclear power plant, once you issue some kind of task and you create the process to run a job, you have to make sure this process should be completed before certain time. And the other real-time operating systems like the operating system in the automobile. So the system actually processes kicked in to determine when we're going to actually take the right turn, when we need to take the left turn, based on the GPA direction. Okay. So these are the different parameters. There's also other parameters like a period and the other kind of considerations, but these are the main parameters we actually use to determine the short-term priority. Now let's take a look at the priority for long-term scheduling. Now remember, long-term scheduling decides when a new process should enter the ready list. So now, because of this, the long-term scheduling algorithm also uses the concept of priority. And we can also use the same parameters as the short-term priority. For example, we can use the arrival, departure, attended CPU time, and real time in the system. Now remember, in the previous slide, we just talked about this for the short-term scheduling, right? Let's say here's a timeline. So now when a process is created, it's in a new state, and then it will be put in the ready state by long-term scheduling, and the running state if the process gets the CPU, and then the process may block itself because it's waiting for a resource, and the resource is not available. And then it will be back to the ready state, and then it's in the running state, and back to ready state, running state, and block it again, and ready, and running. Okay. So by definition, each time when a process enters the ready list, it's arrival. It's defined as arrival. Okay. And the departure is the time when it leaves the ready list and enters the waiting list for a resource. That's departure. And then this is another arrival time because it enters the ready list again. So now, you have a ready, running, that it never leaves the ready list until it's blocked again. So that's another departure time. And another arrival time. So just continue, right? That's for the short term. Now, for the long term, let's draw the timeline. So it's created, the process is created over here. So it's in the new, right? And also ready, running, blocked, ready, running, blocked, ready, blocked, ready, So now, even though we use the same parameter, but the definition for arrival is different from the short term because you have a multiple arrivals for the short term. But for long term scheduling, the arrival time is defined as the time of process creation. So that's the arrival time. And departure time is the time when the process is destructed. Okay, let's say the process is terminated here. So that's the time when process is terminated. So that's the time, that's the departure time for long-term scheduling. So for long-term scheduling, there's only one arrival time and then one departure time. That's the time when a new process is created. That's the arrival time. And at the time when the process is terminated, that's a departure time. Okay, that's the differences. Now, for the attend CPU time, let's say this is a timeline, right? Suppose that we just try to calculate the timeline here. Okay, and then the attend CPU time count from the arrival, the most recent arrival. So attend CPU time is the time after the arrival, and then the time that the process acquires the CPU. So this is the running. This is another running time, but this is a timeline. So that's the attend CPU time. Okay. Now, what's the real time? The real time also is the time from the most recent arrival to that timeline. So you can go back to the previous slide to check the definition. So that's real time. So even though the real time also counts the time when the process is in the ready list, okay, in the ready list, in the CPU, right? Again, in the ready list and the CPU. Okay, so that's a real time in the system. And then what's the total CPU time? It's count from the arrival to the departure. So the total CPU is this and also this. Okay, so that's a departure and that's arrival. Okay, so now the other one is real time, ready list, in the ready list, and that's the time in the CPU. Okay, so that's the total CPU. Now, for the long-term scheduling, so the attend time going to be, in the bigger scale. So attend time going to be attend CPU time going to count all the CPU time, not just this most recent arrival. Also count the arrival of the first arrival. So it will count all this CPU running time. So this is actually the CPU time, and this is another CPU time, and this is another CPU time. So that's the attend CPU time. Not just the most recent arrival. It just count all the CPU time from the beginning, from the time when the CPU is created. Oh, no, when the process is created. Now, what is the real time? So the real time going to be count from the very beginning, from the arrival time, all the way to the timeline. That's real time. Okay, not from the most recent arrival. Okay, for the short term. Now, also the total CPU time, that's going to be counted between the arrival and the departure at the very end. Okay, so that's the CPU time it's used. That's the CPU time. That's the CPU time. And if there's a CPU time used again during that time period, it will be counted again. Okay, so that's the total CPU time. So now, so it's kind of different, but The only difference is the arrival and departure. That's the major difference. The other one, like attended CPU time and real time in the system and total CPU time, the definition is similar because it just count all the, the attended CPU time just count all the CPU times from the arrival. But there's only one arrival, right? There's no such a thing as the most recent arrival. So, okay. So that's a difference between the long-term scheduling. Thank you.